Welcome to our pH video. First, we collected our solutions and placed them into 6 different beakers. Then, we obtained a wash bottle containing deionized water as well as a waste beaker. We obtained pH buffers 4 and 7 for when it became time to calibrate our pH probes. As you can see here, we are calibrating the pH probe with the buffers in order to take the pH values of each solution. The solutions were hydrochloric acid, acetic acid, sodium hydroxide, ammonium hydroxide, apple juice, and orange juice. For exercise 2, we are creating dilutions. 4 dilutions each of hydrochloric acid and acetic acid using a graduated pipette and a 25 milliliter volumetric flask. For the concentrations, we are halving at each dilution. Both acid starting concentrations are 0.2 molar and each dilution will go down 1/2 each. So 0.2 to 0.1 to 0.05 to 0.025. Next, we must make our dilutions for the acetic acid. As you can see here, we are once again using a graduated pipette and a 25 milliliter volumetric flask. Our concentrations for each dilution are the same ones we used for the hydrochloric acid previously. Now we are collecting the pH value for the 0.1 molar dilution. Of course, we wash our probe with deionized water and then place it into the 0.1 molar dilution. Its pH reading was 3. Furthermore, we collect the pH values of the dilutions for the solutions that I listed previously in the video. Here we are working and filling out our pH data and starting a pH versus concentration graph. The graph here is to indicate the difference between hydrochloric acid and acetic acid. We came to the conclusion that the stronger acid was hydrochloric acid. It dissociated faster in water than the acetic acid. However, our graphs ended up looking very similar.
Strong acids dissociate completely in solution, so the proton concentration is equal to the concentration of acid, as the reaction is basically only in the forward direction. Weak acids, however, only dissociate in a small fraction represented by the equilibrium constant Ka. The effect of these acids on a solution's pH, however, can be minimized with a buffer solution. Buffer solutions resist pH change by containing ions that can neutralize some amount of acid or base.
For exercise 3, we place 30 milliliters of tap water in a beaker and then measure the pH of the tap water and add 10 milliliters of 0.2 molar hydrochloric acid to the tap water. We then record the new pH of the solution. We then place a 30 milliliter buffer in a beaker and measured the pH of the buffer solution. After that, we added 10 milliliters of the stock solution of hydrochloric acid to the beaker and measured the pH. The pH of the buffer pre-hydrochloric acid was 4.6 and after was 4.15. The pH of water pre-hydrochloric acid was 7.25 and after was 1.6.